руководителями Грантского.
Манфред Хельмут Байер. Манфред Хельмут Байер, заведующий кафедрой экспериментальной физики Технического университета Дортмунда, Германия. Полный профессор, признанный специалист в области спиновой физики и спектроскопии полупроводниковых наноструктур. В 2008 году Манфред Байер был избран почетным членом физико-технического института имени Йоффе. Список публикаций профессора Байера насчитывает более 250 работ. Многие из них опубликованы в соавторстве с сотрудниками физико-технического института. В 2013 году профессор Байер выиграл мегагрант правительства Российской Федерации, на базе которого в физико-техническом институте имени Йоффе создана лаборатория спинтроники. Манфред Байер является страстным болельщиком футбольного клуба «Боруссия Дортмунд». В последнее время болеет также за футбольный клуб «Зенит» Санкт-Петербург.
The second one will be different from the first one, but I will go directly to the content. So the title of my talk is Spin Physics of the 21st Century, and I want to show you basically two things. The first is that I want to demonstrate you that we believe that it's interesting to study this field of physics. And the second thing that I want to demonstrate you is that we believe that we can provide essential contributions to this field only through the involvement of mega grants and the involvement of a new, still quite new, International Collaborative Research Center that was established last year. So why are we interested in spin physics? There are many motivations, and I want to give just one of them. We are all heavily using equipment like mobile phones, like computers, and these devices relying on information and communication technology, they all use energy. And already in 2010, the energy consumption of these devices was about 10% of the total energy consumption worldwide, and this will ever increase. So the prognosis is that by 2020, 20% of the total energy consumption worldwide will be used by these information and communication technology devices. So a huge energy consumption, we need to provide this energy, and this is clearly a global problem that we have to address, and it might be clever to seek for solutions how we can reduce the energy consumption of every of these devices. Just to give you a little bit more insight, I try to keep it simple. Let's consider a computer. A classical computer in these days basically has two building blocks. The first one is the processor, which is to manipulate the information that the computer shall handle. And the second one is the hard disk, which is for storing this information. And these two building blocks in most computers still are connected by electrical cables. And through these electrical cables, the information is exchanged between these two building blocks. Electrical cables have electrical resistance, and therefore the currents that transfer the information from the processor to the hard disk and back, they undergo losses because of these electrical resistance. So we immediately lose energy, and moreover, the information transfer is fast, but it's not terribly fast. So in more and more computers, and in particular in big computers, these electrical cables are already replaced by glass fibers. And this is done for good reasons, because now the information is transferred from the processor to the hard disk and back through light pulses. And light pulses, they do not feel any resistance in these glass fibers, so this information is transferred without any loss of energy. Moreover, light propagates at the fastest speed that you can imagine, so this exchange of information is very, very fast. Still, in order to generate these light pulses, you need lasers, and lasers need energy. So we might want to go a step further and reduce the energy consumption even further. So one strategy that one might think of, why still use two separate building blocks, the building block of a processor and of a hard disk? Why not just combine them into a single building block, where we have an all-in-one chip solution, as people say, and then you would have a single device with which we do manipulation and storage of information. So this seems to be a clever idea. Now we have to think, how do we store information in order to realize this? And information, of course, in these days is stored in digital form, so by a sequence of zeros and ones. And for storing information, we therefore need a physical representation of 0 and 1. And this is obviously done, simply speaking, by magnets. And a magnet can be oriented up, this would be the 0, or it can be turned around, can be oriented down, this would be the 1. And this is the way how we store information on hard disks. And during the last 2 decades, people working in this field have done nothing else than miniaturizing these magnets, simply speaking, making them smaller. And by making them smaller, you can basically store more and more information on the same area of the hard disk. So this is just a dense packaging of information. Now, continuing this trend of miniaturization, one might think, what is the smallest possible magnet that you can imagine? And this smallest possible magnet is an elementary particle which carries an excitation which is called a spin. And the spin can also point upwards, this would be the 0 for storing digital information, or it can point downwards, this would be the 1. So the ultimate goal would be use the spin of such an electron to store information and also to manipulate this information. And as we have learned from these glass fibers, it might be a clever strategy to do this by optical means. So, how do we, now that we know how to store information, how do we manipulate information? This is shown here. So we have a sequence of bits, and I show you here the classical way of manipulation of information. So we have 3 bits here in this case, oriented such that we have a bit sequence of 0, 1, 0, and the classical way of manipulating this information is just to address this bit sequentially. So for the manipulation that we want to do, we address first bit 1, and for the operation that we want to perform, we invert it so that it's converted from 0 into 1. And then we turn to, afterwards, we turn to bit 2, which is in the 1 state. And for the particular information, we don't want to change it, so we leave it as it is. Then we turn to bit 3, we want to manipulate it, we want to invert it and turn it into state 1. And through this sequential operation, we have converted this bit sequence from 0, 1, 0 to 1, 1, 1. Now, can we do the same with the spin of an electron? Of course we can do this, but the spin of an electron can do more, because it's a quantum excitation, and then we have new life. We can orient the spin upwards, this would be the 0 state. We can orient the spin downwards, this would be the 1 state. But the spin as a quantum excitation is a physical representation of Schrödinger's cat. So as Schrödinger said, in this orientation the cat would be alive, in this orientation the cat would be dead. But since it's a quantum excitation, it cannot only point upwards or point downwards, be dead or alive, but it can point basically in every possible direction. This means that the spin can be, the cat, can be simultaneously dead and alive. Okay, so this is the famous Schrödinger's cat, and this opens totally new perspectives. These are shown here. We have again now a bit sequence, 3 bits, which are called now quantum bits, and on purpose we introduce now interactions between these quantum bits, as indicated here by these wavy lines. And if we do it in a clever way, we can do the manipulation of the quantum bits such that simultaneously operation is performed on all these bits, and all of them are sort of rotated in a single operation into this desired orientation. So this would be not only a sequence of operations, but this would be massive parallel processing by which we could also reduce the energy consumption. And obviously this would be an enormous increase of processing speed. And this is the basis basically of quantum computers, which have the potential to solve problems that we up to now cannot solve with classical computers. So this is one of the motivations why we are interested in spin physics. And actually, this coherent spin physics is the central topic of 2 mega grants. The first one is the SOLAB, and the principal investigator is Alexei Kavokin, our distinguished chairman from St. Petersburg State University. And the second mega grant is the hybrid spin optronics lab, for which I'm responsible at the Joffe Institute. Our first task was to establish at these institutions, so to speak, state-of-the-art, world-class laboratories. These are photographs of these laboratories. This is finished by now, and what I should point out is that these two mega grant laboratories are installed such that their expertise and their facilities are largely complementary. So there is a natural interest to cooperate between these two mega grants. And at this point I should mention that we also collaborate with an additional mega grant, the so-called Ferrol's Lab, which is also located at the Joffe Institute. So what were our goals or our mission of these mega grants? Of course, we could distinguish between short-term goals and long-term goals. Two short-term goals, of course, we want to use this excellent world-class equipment to train a new generation of young scientists, which we do actively. And by doing this, we simultaneously perform research, which hopefully is also world-class. In our case, would be published in leading international journals. Then we, of course, have also a long-term goal. So far, we are doing mostly basic research, but our goal is, of course, to transfer this basic knowledge on the long run also into the information and communication technology of the future. We hope that this will happen very fast, very soon, but we are also aware that this can take some time, and therefore we also need substantial long-term support. Just to give you one classical example, the television, the TV. The basic ingredients of TV were basically around about 1900, but still it took 50 to 60 years to bring them in every household. Yeah, now every household has a TV, but this took about 60 years. Hopefully we will be faster. So far we succeeded in securing short-term support. This is provided by the mega grants. Also mid-term support. This is provided by an international lab that I will come to in a moment. And we are fighting to get long-term support. So what is this International Collaborative Research Center? In German, this is called a Sonderforschungsbereich. This is the first such center that was ever established between Russia and Germany. The basic financial funding is provided on the Russian side by RFFE, Russian Foundation of Basic Research, and on the German side by the German Science Foundation, Deutsche Forschungsgemeinschaft. It's operational now since 2015, and the budget for 4 years is 700 million rubles, so 10 million euro, which is substantial. And the good midterm perspective is that it can operate up to 12 years. The involved institutions are St. Petersburg State University, the Joffe Institute in St. Petersburg, and my home institution, Technical University of Dortmund. What is the topic of this initiative? The topic is coherent manipulation of interacting spin excitations in tailored semiconductors, and this basically expresses exactly our vision that we want to follow, namely that coherent manipulation means nothing else that we want to do this manipulation in the most energy efficient way that we possibly can do. So thereby we reduce the energy consumption, and for doing this we want to introduce novel content. For example, this concept of interacting spin excitations, where we do no longer manipulate on the bits individually, but we introduce targeted, tailored interactions to manipulate on them simultaneously, and this provides or is provided only if we develop new materials, and this represents also a novel concept in material science. So some features of this initiative is we are not only interested in information and communication technology, but we are also interested, for example, in healthcare, because spin physics is also the basic of magnetic resonance spectroscopy, and we are convinced, we are almost sure that we can improve the sensitivity of current magnetic resonance spectroscopy by at least 3 orders of magnitude. So when you think about hospitals, investigation for cancer or things like that, this would mean that you can detect a tumor which is 1,000 times smaller than you can detect it today. And obviously you can start treatment very much earlier. So this is definitely life-saving. A few other features in this initiative, we have also a so-called international or integrated research training group, which basically means that every German PhD student has to go for 6 months to St. Petersburg and work there, and vice versa. Every Russian PhD student has to come for 6 months to Dortmund, not only to watch soccer, but also to work on physics. There is strong interest in this initiative in both countries, in Russia and Germany, and I should point out that we have also a lot of international collaboration requests from leading centers worldwide. This is the official logo of this initiative. This is the alternate logo of this initiative designed by Alexei Karokin, where you see again Schrödinger's cat. As I said, the laboratory is now up and running. We have the first results. I think we performed quite well because we could submit and publish these results in leading international journals. And I have no time to go in all the details of this work. I just want to highlight very briefly one result that was published this year in Nature Physics, which brings me back again to this topic of this initiative, coherent manipulation of interacting spin excitations in tailored semiconductors, and emphasis here is on interacting, because we need robust interactions between the spins. And between spins, the decisive interaction is the exchange interaction. I don't want to go into any details, I just want to give you some features of this interaction. Standard exchange interaction between spins relies on the overlap of atomic orbitals. Atoms are terribly small. So this interaction is effective only over distances of a nanometer or so. Very small distance, a billionth of a meter. Now we have discovered a novel exchange mechanism in so-called semiconductor metal hybrids, where the distance over which this interaction is effective is 40 times larger. 40 nanometers instead of 4 nanometers. You might still say that this is a terribly small distance, but the decisive thing is now when you think about nanostructure technology, it is extremely difficult to fabricate structures with these dimensions, while by state-of-the-art nanotechnology, it is no longer a big problem to fabricate structures with these dimensions. So we believe that this is a huge step forward, and this brings me to my conclusions. I believe, or I'm convinced, that mega grants have provided a mega boost for the research in Russia. In our case, 2 mega grants are involved, SOLED and hybrid spin optronics, and this was the basis, and it was essential for establishing this new international collaborative research center between Russia and Germany. And the fundamental basis of all these activities is really the reliable partnership among long-term friends. All the people involved collaborate now already for 25 years. And I pointed out already that we have secured now short and mid-term funding, but of course we want to work on a long term. So our vision is sort of to establish a joint Russian-German Institute for Spin Technology of the future. And with this I want to stop and thank you for your attention. Спасибо большое.